So in this video, I want to show you a few more techniques for solving trig proofs. Remember that there's not sort of one size fits all, right? There's not one strategy that works for every proof. What we're trying to do is build up our toolbox so that when we see a new proof, we have a few more resources to draw on. So just to remind you of some of the tools we've seen already, one technique is if you see a tan theta somewhere, you should probably use the quotient identity. It's probably a good idea to replace that with a sine theta over a cos theta. That works a lot of the time. And if you see something like a 1 minus a cos squared theta, it's probably a good idea to use your Pythagorean identity. You have to do a little bit of rearranging there, right? Your Pythagorean identity is this: cos squared theta plus sine squared theta equals 1. But if I move the cos squared to the other side, I would get sine squared theta equals 1 minus cos squared theta. So I could take that whole 1 minus cos squared theta and just replace it with sine squared theta. The same is true if you see something like this, right? If I saw a 1 minus sine squared theta somewhere, I'd probably want to use my Pythagorean identity here to do something like this. I know cos squared theta plus, sorry, this is squared, sine squared theta equals 1. So if I move the sine squared to the other side, then cos squared theta is 1 minus sine squared theta. So it probably makes sense to replace all that 1 minus sine squared theta with a cos squared theta. And the other technique that you've seen so far is getting a common denominator. So you've seen how if I have sort of two things, maybe a 1 over cos theta plus a 1 over sine theta, it might be a good idea to combine those two fractions using a common denominator, especially if that's on the left side and the right side is just a single term. And that tells me that somehow those two fractions did get added together, right? So that's a good tip off to use the common denominator technique. But in this case, none of those things apply, right? There is no 1 minus cos squared theta or 1 minus sine squared theta. There's a 1 minus cos theta, but that's not the same thing. So I can't just replace that with like sine theta. That's not true. There's no tan theta, so I can't do a sine theta over cos theta move. There's not two different fractions to add together. There's just one fraction on the left side, one fraction on the right side. So none of the techniques we already know will work here. So just erase them all. We need another technique. And the new one I want to show you here is called making a difference of squares. So this is a useful technique for any time you have either a 1 plus cos theta, not cos squared, right, just a single cos theta, or 1 minus cos theta, or similarly if you see like a 1 minus sine theta, or a 1 plus sine theta. If you see these sorts of things, then getting the difference of squares might be a good idea. Might not work, but might work. So that's what we're going to try here. First move is always separate your left side and your right side. So your left side is 1 plus cos theta over sine squared theta. And your right side is 1 over 1 minus cos theta. I usually work on the more complicated looking side first, and it looks like the left side's more complicated. So we'll start by simplifying that, but you can actually solve this proof either way. You can start by working on the right side. Oh, I forgot the S there. Right side first too, that would be fine. All right, so what we do, whenever we see something that looks like a 1 plus cos theta or 1 minus cos theta, so that's why I said you could start by working on the right side too. What's a good idea is to create a difference of squares. So how we can write that is actually rewrite it like this. So I'll keep my fraction there. What I'm going to do is multiply the top in brackets by 1 minus cos theta. So the same thing with the opposite sign. If I do that to the top, I have to do it to the bottom, right? That's just required there. And what I've done here is I have a difference of squares now on top. I have a 1 plus cos theta, 1 minus cos theta. That is actually a difference of squares. And that can be helpful because let's see what happens when we actually FOIL that out. So foiling that out will look like this. I'll do the first, right? So the 1 times the 1. That gives me just 1. Then I'm going to do the outside. So 1 times negative cos theta. That gives me a negative cos theta. Then I'll do the insides. So the cos theta times the 1. That gives me a positive cos theta. And finally, I'll do the last. Cos theta times negative cos theta. Well, that would make negative cos squared. theta, right? Cos times cos is cos squared. And what you'll notice is with the difference of squares, those middle terms always cancel out. So negative cos theta plus cos theta, those guys are gone. And you're left with just 1 minus cos squared theta on top. Now don't forget there's still a whole bottom here, right? There's still a sine squared theta here. And this whole 1 minus cos theta, like we haven't touched that, right? That's still all there. But let's rewrite out our top again. Now it's just 1 minus cos squared theta on top. And on the bottom, I still have that sine squared theta times 1 minus a single cos theta. These guys do not cancel with each other. So the 1 minus cos squared theta does not cancel with the 1 minus cos theta. Those are different things, right? If this was 1 minus cos squared and that was also 1 minus cos squared, they would cancel. But the one has a squared in it, the other one does not. So they're not the same thing. There's subtracting or adding on top and subtracting or adding on the bottom. So you can't cancel even like the cos squared. The cos isn't going to be allowed because of the subtraction there. So I can't touch that. But what you might be noticing already is that 1 minus cos squared makes you think of your Pythagorean identity. So your Pythagorean identity would tell you that 1 is equal to sine squared theta plus cos squared theta, which means that 1 minus cos squared theta will equal sine squared theta. So I could replace that whole top with just a sine squared theta. So let's do that. So the top will become sine squared theta. And then the bottom is still sine squared theta times 1 minus a single cos theta not squared there. And now you can definitely notice what's going to happen next. I have a sine squared on the top and a sine squared on the bottom. No more weird adding and stuff in there. Right now everything is multiplied on the top and multiplied on the bottom. So those will actually cancel out. And that simplifies, I'm running out of space here, but that simplifies my left side to be just a 1 on the top, right, now that that sine squared has been canceled. And on the bottom, I'm still left with a 1 minus cos theta. All that work, but then I look over at the right side and notice that actually that's exactly what the right side is already. So I don't have to do any work to the right side. I can say left side equals right side, and we're done. We solved our proof. All right. Let's try another one. So here's one where we're going to need to use the distributive property. So our first move is just to write down the left side and the right side. So the left side looks like this. And the right side looks like this. Draw a line in between them because you know nothing is ever going to cross that line. And then we're going to work on this left side here. The first thing I would do is if you see any reciprocal trig functions, just straight up replace them with the regular trig functions. So as soon as you see that secant theta, replace that with a 1 over cos theta right away. Most proofs are much easier if you use sine, cos, and tan than if you use secant, cosecant, and cotangent. So that's going to be a really good first move. The next move is this new technique of the distributive property. So if you see you've got like something outside the brackets and then some brackets here, you might want to think about multiplying that in there. That might make it simpler for you. Now sometimes that doesn't actually make it simpler, but often it does. So let's do that. So distribute your cos theta in here. I would get cos theta over cos theta for my first term here. And my second term is going to be cos theta times cos theta, and that is cos squared theta. Well, I can simplify this a little bit more, right? Cos theta over cos theta, that's just 1. So that first term becomes just 1. I get 1 minus cos squared theta. And that should make you think of your Pythagorean identity, that 1 minus cos squared theta is actually equal to sine squared theta. All right, so it looks like we've really simplified the left side, so let's leave it alone. Go over to our right side. Our right side, if we see a tan theta hanging out, almost always a good idea to replace it with the quotient identity. So if you see a tan theta, use your quotient identity, which is tan theta is sine theta divided by cos theta. And then you have a cos theta here on top and a sine theta on top as well. Notice that you've got a cos theta on top and a cos theta on the bottom, so those guys are going to cancel out. And then you have a sine theta times another sine theta. Well, that makes sine squared theta. And so we've succeeded. Our left side and our right side are the same. So you can say left side equals right side, and we've made it to the end. All right, one more example with some new techniques. This one we're going to use both factoring and foiling. So both sides are pretty complicated, so we're going to have to simplify both sides in this case to get them to look like each other. We'll start out by writing the left side on its own. So the left side is sine theta minus cos squared theta times sine theta, all divided by sine cubed theta. And over here, the right side is sine theta minus cos theta all squared, and then plus 2 sine theta cos theta. All right, so draw your line down the middle. We'll start by working on the left side here. So what you can notice on the left side is that there's a sine theta in both terms on the top, right? There's sine theta and then minus cos squared theta sine theta. So there's a sine theta, that's not a sine zero, sorry, that's a sine theta. So a sine theta here and a sine theta there. So here's where I'm going to use a technique of factoring, right? So I could factor a sine theta out there, and let's see what happens when I do that. That gives me sine theta on top. And when I factor a sine theta out of the first term, I would just get 1. Factor a sine theta out of the second term, I would get a cos squared theta. All right, and then that's all over sine cubed theta on the bottom. Cool. But now also notice that 1 minus cos squared theta should make you think of your Pythagorean identity. 1 minus cos squared theta is actually sine squared theta. So that top should simplify to sine theta times this whole thing. 1 minus cos squared theta is just a sine squared theta. And on the bottom, I still have the sine cubed. Now you can use your exponent rules. So I have sine to the power of 1 times sine squared on the top. That's going to make a sine cubed on the top. And on the bottom, I have a sine cubed as well. So in this case, the top actually cancels the bottom completely. And this simplifies just to 1. Sine cubed divided by sine cubed is just equal to 1. All right, now we have to make the right side somehow look like 1. Right now it doesn't look anywhere close to that. But on this side, we're going to use the technique of foiling. So if you see like something like this, like a sine theta minus cos theta, and then it's squared, that means I should probably FOIL this out. That's usually a good idea. So I'll write it out like this. Sine theta minus cos theta times sine theta minus cos theta. And then I've still got this like plus 2 sine theta cos theta at the end here. So just write that in. So for foiling, we're going to need to multiply our first terms first here. So the first terms, sine theta times sine theta, that's going to make sine squared theta. Next, you're going to want to multiply your outside terms, so sine theta times negative cos theta. So it's going to be negative sine theta cos theta. And then your inside terms here, so that's these two. Negative cos theta times sine theta, so it's another just negative sine theta cos theta. And then my last term, negative cos times negative cos. Well, that will make a positive cos squared theta. And then I still have this at the end, right, my plus 2 sine theta cos theta. All right, notice what simplifies here. I have the same thing 3 times, I've got a negative sine theta cos theta minus another sine theta cos theta plus 2 sine theta cos thetas. Well, what does that make? Negative 1 of something minus another 1 of something plus 2 of it. Well, those actually completely cancel out, right? Like negative 1 plus 2 of the same thing makes 0. Those are gone. And what are you left with? Well, just the sine squared theta and the cos squared theta. Everything else is canceled. But that makes you think, hopefully, of your Pythagorean identity. Your Pythagorean identity is that 1 is equal to sine squared theta plus cos squared theta. And so, if I have a sine squared theta plus cos squared theta, that side must equal 1. And what we've shown is our left side and our right side are equal to each other, And so we are done this proof.